All right, now that the recording begins, let's cover the material today. So, uh, last Thursday, we kind of like start diving into functional programming, specifically this language called Scala. Today we will actually continue on from what we covered on last Thursday and talk about this thing called pattern matching and tail recursion. So a quick recap, right, on what we learned from last Thursday is uh, one of the main thing that is different in terms of functional programming versus the iterative programming such as Java, C, Python that you've been doing is we handle repetition with recursion. Some of you will hate it. I would assure you some of you will hate it. When I learned this for the first time, please trust me on this. I absolutely hate this. So I totally understand how you feel about this. But if we can write a loop using recursion, it gives you ability to actually perform many mathematical related things. Because recursion is a function call, right? It's a function call with some termination, like basically termination condition at the end. If if the input equals 0, you're done. You start returning, right? So these are how you can write loops with recursion. The in-class exercise 2 and in-class exercise 3 are designed so that you can actually practice using both data structure and recursion at the same time, right? So we already released in class 3. In class 4 would be listed right after we're done with the lecture part today. I haven't actually put it on the in-class assignment on Canvas yet. I will do this right away because the bullet points on and the explanation of what you have to do is at the end of this lecture. So what do I mean? Basically, if you want to write a function that loops, right? You basically specify the function input as well as the return type. And return type in case it's if it's a recursive function, you need to specify what do I return. Why is that the case? Because this return type is used for the whatever function is called this. Recursion is about calling functions again and again and again, right? So you need that return type. Another concept that we cover is the concept called tuple, which is basically a collection of items. It's a fixed number of items. Each can have different types. And as we discussed last Thursday, someone brought it up. It has to be order, and that's absolutely true. It has to have certain order. Hello, 1, you would have to have this strict order, a string followed by integer. We introduced a type of tuple called a pair. And for a pair, a rule is actually really simple. If you have the value v1 that bind with expression e1, value e2 that is evaluated from expression e2. A pair e1, e2 will evaluate to v1 and v2. And the type of the pair would be the same type of the whatever expression you have. So T1 and T2. And you can bind a pair to a name because we want to be a little bit easier on calling things, right? You don't want to say, hey, that pair hello and 1 over and over and over. You can say val t equal hello and 1. The next time you use t, Scala would know, okay, that's the pair hello and 1. So you can bind a name to a pair. You can access each of the components by using the dot underscore and the number. Number 1 means the first item. Number 2 means the second item. Number n means the nth item, right? So you can use this to unpack the pair. You can do val a b equals t. In this case, a would take hello, b would take the value 1, right? So this is basically how you can use a pair. And then we talk about a list. And please, for this week and last week, this is one of the slides that I really want to make sure you get it. Because you use lists a lot in this class. Anyone here remember this thing called array? Yes, no? our old friend array. And that's basically a tuple, right? You know the size. But if you want to expand your array, one thing you can do is use a list, right? So this is like your old friend dynamic array and your old friend linked list. Um, when you type in list with the parentheses, basically that makes an empty list. You can define the type of this list using, again, colon. Colon means I'm going to specify the type. And you can also make the list with elements into it initially. Like list 1, 2, 3, 1, 2 will make a list that consists of 5 items 1, 2, 3, then 1, and then 2. And you can stick elements to the front of the list because list in scalar is front, basically modified at the front, right? And it means you're going to get a brand new list. Again, we'll talk about immutability properties later on in this class. Just remember, when you have a new list, it's not the same old list. So if you use list of T, right? T equals 1, 2, 3, 4, 5, and you say you want to append 6 at the top, at the front, T, our name T will still point to our old list 1, 2, 3, 4, 5 because you get a new, totally different list. Specifically, if E1 is the front of the item, evaluate to the value V, E2 is our list. If you want to append E1 and E2, you have the same type list of T, but it would now represent that old list, then you have the new item append at the front. And we talk a little bit about pattern matching. We'll talk more about this today. You can do pattern matching using the keyword match, right? The keyword match allows you to do something like this. You have the input list, and you use called XS, and you use pattern matching to break XS into different cases. What form can XS act as text? It can be an empty list, just new. You initialize the sum to 0. If not, you just add the head to some list of T, right? This allows you to pattern match the list with each of the case that you have. And the benefit here is basically to give you warning if you're missing any specific cases, making sure your program is likely to be correct. Give you warning if you have duplicate cases. It makes things more concise and easier to read, right? And this is important when I'm grading, well, not just when I'm grading your assignments, but in real life. How many people you read your friend's code and you have no idea what they're trying to do? Like, let's say you're in the lab, right? Your friend's like, oh, I'm stuck with this assignment. I'm trying to figure out how to do this. Can you help me? And then you look at their screen, it's like, for the love of God, I can't understand what it's trying to write here. How many times does it happen to you? Yeah, and I see some thumbs up, right? And that happened to everyone, right? Sometimes you finish your assignment before your friend, sometimes your friend did it before you do. So you discuss and figure out together how to actually help each other without plagiarizing. There's a border, like there's a strict line between the two, right? So assume that you just basically help teach and guide your friend. You look at their code, trying to figure out for this code block, what is the exact algorithm that your friend is trying to do? And you're suffering. That's sometimes because your code is not as readable as you want it to be. Because you write it yourself. You know exactly what does each line do, but your friends is not. Pattern matching allows you to basically be a little bit more systematic into, okay, if the list is empty, you do this. If the list is not empty, you do that. If the data in the tuple behave this way, you do certain things. And today, we will do more of the pattern matching by, I'm gonna show you a code here. And let's figure out this code together. Why is this code bad? There are actually multiple things. So let's actually figure this out together. And some of the hints are in the comments already. I said this is a bad idea. Some of the hints are in red. So let's talk about that. let's actually spend the next like 5 to 10 minutes talking about this code. Why is it bad? Anyone want to take a stab at some of the things I did here on the code and why it can be bad? One thing for sure, the two cases return the same thing. So that's one of them, for sure. So thank you so much. And again, by the way, this is one of the features I love in WebEx, and it's not available in Microsoft Teams. Private chat. So if you want to answer my question or ask anything or like just tell me I don't understand what I say, do that in a private chat. If you don't want to expose who you are to your friends, please do it. I don't mind at all, right? I want to maximize your learning experience. If that helps, do it. So one of the private chat is there are two cases that return the same thing. Yes. Uh, and another comment is you could definitely change this thing, which is this is something we're gonna do as well. So that's that problem. So let me say this is a second thing that we pointed out. This return the same thing. This is the first thing we pointed out. Anything else? So a quick hint for all of you. How many times do we actually have to call badminton in many cases? So look at this two input A and input B. The way you call the function, same list, 1, 2, 3, 4, 5 to 30. So if we put in those two lists, one start from 1, 2, 3, 4, 5 and count up, the other list, 30, 29, 28, count down, right? We have these two lists. It will return the same number, which is 1, right? Because that's the minimum number in my list. Which one is worse? And why? And kind of stress on this bold red text, right? All right, hint. How many times do we have to call badminton? So what does this function do? What does this badminx.tail do? What does it try to do? It's trying to find a minimum, right, of something, right? All right. Can you say something or type something in? Just want to make sure everyone is still at the same page here. All right, give me a second. Someone call me, so let me get this done. สวัสดีครับครับพูดอยู่ครับ All right, so you see that we have two function calls for badminx.tail, right? Do we need to call badminx.tail twice? This is basically to find the minimum, right, of xs.tail, right? So let's say this is xs. 5, 10, 2, 3, 4, right? And this is xs.tail. It's basically find the minimum number as that of that xs.tail. So what's the problem with this? Do we actually have to call this function twice? So can someone answer whether we have to call this function twice in this big function? Yeah, I mean, to be honest, you already found the bad. Like if you do this, you already know, right? You already know what is Batman XS.tail. Why do you have to repeat the same function call again? It's wasting your time, right? Every line of code that you put in your program, you're telling the computer to do something, right? You are wasting the CPU time because you call Batman twice. The computer will, I mean, they're not gonna hate you. They'll do exactly what you ask them to do because that's what the computer is designed for. You program them. That's the definition of programming. You program a computer to do certain things that you're writing, right? Do you have to actually do it twice? No. Yeah. So what can we do? Let's look at a better code. Right. Let's look at this better code. We'll keep the top thing. We will actually fix it later. But at the end, you can call this minimum function once and store them. Basically have this temp variable to say, hey, that's the minimum of the tail, right? And if the head is even lower than that, you're going to return the head because that's the minimum, the new minimum, or you return the old minimum, right? Any questions so far? So this is one of the example of how you can minimize the amount of work that you have to do. And this is another thing that you have to a little bit be careful with functional programming, because when you think about everything in recursion and you treat function as the first class citizen, sometimes you just call recursion everywhere. Don't forget that when you call a same function call everywhere in that big code, it actually will execute all of them, right? So it's gonna waste some of your time. So this code now call the function once instead of twice, so you save a lot of time. This is where pattern matching comes into play. We still have that red text. If XS is empty, we will just initialize that to a maximum, right? So is that okay? It's a bad idea. But at the moment, we don't have the tools to actually solve it, right? How many times you write a code in C or in Java or in Python and in any of those where you want to call and find the minimum value? You want to find the minimum of the array, right? Array called array A. And then you do int minimum equal the maximum value of integer, and you go from there. How many times you have to write a code that way in C, in Python, and in Java? Anyone did that? Otherwise, your code had bugs for sure, because the initial minimum is not the most like the highest value that you can have, right? Is that confusing, by the way? Should I do an example? So let me write a code in C, right? And then what you would do is basically for I equals 0, I is less than size of A, I plus plus, right? And then if A of I is less than minimum, you then say minimum is A of I. You update minimum, right? You can set it to the first element as well. So that's a great alternative, right? So another way you can do this is to do minimum equals A of 0. What can be a problem of that? What if I never have A of 0? What if A of 0 is empty? Which is exactly this case, right? But it's exactly that case. In that case, well, what are you gonna return? It's okay in C, right? You can return the maximum value and you can return an exception, right? Let's actually treat this and use another construct that can help basically mitigate this problem. This is called an option, right? What does option mean in real life? Can someone define the definition of option? It's a choice, right? Options mean we have a choice. Option is a type. It's a data type in Scala. It's actually generally in functional language there'll be something similar to an option. And as you said in the private chat, it means you have a choice. Think of it as option of type T is either none that express emptiness. There's nothing here, right? And sum of T, where the type will be type T and the value is the value V. So this is a new data type, right? Anyone here use something similar to this before? If not, awesome. We will learn something new and exciting. In data structure. Okay, awesome. If you have used it in data structure before, same concept applies, right? So let's see some usage and example. I can initialize x as an optional string that equals to none, y as an optional string that equal to sum of high. This gives both x and y at the same type. X and y, you can do x equal y. You can check if x is the same as y because now it has the same data type. But if you somehow have this microscope, actually I never used Swift before, so that's a great question. Let me double check. So the question is this the same as optional on Swift? So let me actually check. Can you remind me later after we're done with today's lecture, the lecture portion when we're in Discord? I'm gonna look it up and address that because I actually truly I don't know. I never used Swift before. I'm sorry, but I will make sure I check it out and see if that's a yes or a no. Anyway, these kind of question is awesome, right? So because it's not just you learn something new, I learn something new too. Okay. Uh, Anyway, so option means that you have an option to actually express like our value into something that has the actual value or this black hole that contains nothing. Okay, that sounds a little bit grim and depressing. So I'll stop at that. You can define an option with different types. So what is the type of this option? It's an option of a pair which consists of a double and a string, right? So you can say option of double and string equals sum of 3.14 and pi, right? Q is equal to option of the list. This means that my list I can have a list or I don't have a list, such as this, right? Now you're wondering, since you have an option now, so how do I access the value of y, for example, right? I have y, I want to access this value of y, which is basically high. How can I get high? Because if you just type in y, if you type in y, this would evaluate to sum of high. So if you have another variable called a equal hello, right? Let's say a evaluate to hello. You can't really compare y and a. Why is that? Anyone want to guess why you can't just say y equals to a? And this is going to be something that you're going to run into in the first assignment, actually. Why I can't say y equals to a? Anyone want to take a guess? So what's the type of y? What's the type of y? because it's so that's actually I think you're getting to I think your understanding of it is correct. Maybe that's awesome actually. So both answers are in the correct direction. The specific answer is the type of Y is sum of string. Is an option of string. Y has a type option of string. A has a type string. And in functional programming, most of the time it's a really, really strongly typed languages, which means that if you have an operation like equal equal, you have to have the same type on both sides, right? The left side here is sum of high, which is an option of string. The right side is a string. You can't compare them because the computer doesn't know how do I compare option of string and a string. It's kind of like if you have to compare and I'm trying to find fruits that's not the same but similar. Uh, like durian and jackfruit. They both have this big fruits, right, with the thorn around it, and they're both delicious, but they're not the same fruit, right? So you can't compare them. To actually be able to compare Y and A, at the end of the day, okay, someone ring the bell on my house. Let me get that quickly. I'll be right back. I'll be right back. All right? Like, give me 1 minute. All right, I'm back. So basically, to actually extract the value high, right, from the option of t, you can do that. So let's say if t is an option of t, then t dot is empty is a function that would check if t is empty or not, right? T dot is empty would give you true or false. If t is not empty and sum of v that has type t, then the function that called t dot get will give you v. So from the earlier example, you have y equals sum of high, right? What is the value of y dot is empty? Can someone tell me what's the value of y dot is empty? Is it true or is it false? Is y dot is empty true or false? Yeah, it should be false, right? So what should be the value of y dot get? If I type in y dot get, what should I give? What does that evaluate to? Would that be sum of high or just high? Yes, exactly. You're correct. So it should be just a string high, right? So that's how you can compare. Basically, you break down the sum of parentheses, check it out. I now have the value, right? So if the the option is actually empty and you do t.get, let's say I declare another variable called b equals none, and I say b.get. This would give you an exception, right? So to avoid this exception, another function you can do instead of t.get, you can do t.get or else, get or else. This is similar to t.get, but if it's empty, the expression would evaluate to these variables that you put in here. When empty is an input to this function. If t is not empty, you're going to get the value. If t is empty, it will return this thing. And you can basically put whatever that thing is. Pattern matching also works with option. So you can do x.match. Let's say x is an option. x, your input here, is a function that just increment x by 1. But in this case, x is, for example, sum of number 5, right? This means that I have number 5, but it's an option of integer, not just a flat out integer. So this means I want to increment sum of 5 into sum of 6, right? So x is my input. Input is an option. So what should I return? I should return an option of int, right? And then do pattern matching. If x is none, x is a black hole. It doesn't really have any value. What will happen if I increment it? What should I return? I'll just return the same thing, none. If x has a value, I can then return sum of 1 plus that value, right? So you see how pattern matching can make this work. So let's fix our old friend finding the minimum function called bettermin, right? Let's get rid of that one weird case in the beginning that has x is empty. And this is the modified function. Let's go through this together, right? Let's go through this together. X is now a list of int, right? A list of int, and it now return an option of int. So that's a difference. This is the first difference. Instead of returning an integer, which is the minimum, now you return an option of integer because we'll use an option for these purposes so that if x is empty, you can return this none. Well, when my input list is empty, so I'm not gonna return anything. It's none. Else, you first evaluate what's the minimum of xs.tail, right? Because now you know that xs has something in there. So you're gonna do a betterment of xs.tail if this is not empty and the answer is lower than the head. Basically, you're comparing the first item here and the minimum of the rest of my list, right? If you compare the two, and if this is lower, you return tl.answer because it's already returning an option of int. So tl_ans is the minimum of the tail list, the rest of my list. Instead of returning a number, it now returns an option of that number, sum of that number. So you need to do tl_ans.get. Okay, let me erase that multiple circles that I draw to make it clear, and I use a different color, right? I have tl_ans. tl_ans is sum of something, right? It's a sum of number, and that's a minimum number in my list. To get the number, because you want to compare this to a number, this is an integer, right? This is sum of integer. That's why you need to do .get to make it an integer so you can do the comparison. Once you can do the comparison, you either return the minimum of my list or the front, which is sum of xs.head. And now you can actually separate out the empty and non-empty cases later, right? But any question on this code for now? Any question on this code? So I'll give you 1 or 2 minutes to look at this code. Feel free to ask me questions. By the way, oh yeah, so dot gets force an option to unwrap. Yes, exactly. That's a great word. So there's a private comment about so dot get forces an option to unwrap into the type that's specified. That's a really perfect example and definition that I should have used actually. Thank you. So basically, yeah, it's unwrap the option into the internal type. In this case, the internal type is integer. So .get would just break the shell and wrap this option into an integer. Awesome. By the way, quick thing. Since this, I think this, my neighbor is probably fixing the house, so if it's loud with the hammering noises, let me know. I will figure something out. Uh, I hope it doesn't really go into the microphone, but I can hear them. There was a time last semester in system skill where there's like the local government was digging a hole in front of my house and no one can hear what I say. So I hope that's not the case. Anyway, so now that we have an example and assuming that you have no more questions, if you have questions, feel free to type it in, or if you want me to slow down, feel free to let me know. But let's further fix this function betterment so that we can now handle the empty case and non-empty cases, right? And here's the fix. So if xs is empty, again, we return none. Okay, my list is, there's nothing in my list, so I'm gonna return none instead of return some fake minimum, right? Otherwise, def min non-empty. So this is the non-empty case. If ys, which is an input, is a list of integer. If list ys, our list ys dot tail dot is empty, what does it mean? What does ys dot tail dot is empty really mean if you look at the list? Will that be true? When will that be true? When will that be true? The question is, when will this become true? When the whole list has been processed and you only have one thing left, right? This is only true if you only have one thing in your list. Right? Basically, that whole argument is ys only have one item. If that's the case, you return the head, right? Because that's the only thing in your list. You can return it. That's the only thing for sure. That's the minimum, right? Otherwise, you get ys dot tail, get the minimum of ys dot tail, and you compare and return. So this basically further optimize your program slightly, right? Slightly. By first, if my list is empty, take care of that. If the list is not empty, here is a recursion for our non-empty list. Do you see that now inside the blue text? Inside the blue text, there's no option. Everything is just a list of integer and an integer, right? So this is another way you can implement finding a minimum value, right? You first break it into none and the case where the list is not empty. If the list is not empty, deal with it. You don't need even an option for that. At the end, you just need to make sure you return some of min non-empty, I guess. Right? Sure, yes. So the question is, can I explain the sum again? So this sum and none is a concept called option. So an option of a type, let's assume our type is integer, but this applies to any data type, right? Let's assume for now you deal with integer, right? Are you with me so far? All right. So options means you have a choice. What choices do we have, right? You with an option, with a data type called option, you have two choices. You can have none and some of integer. It basically means that your data can take two forms. The first form is nothing. The second form is an integer. Basically, these give you a way to express the fact that sometimes you don't have the input, right? So let's say your input is supposed to be an integer, but you have the edge case where Sometimes you don't have an input. What can you do? You can use this option as a solution for that. So are you with me so far? Basically, it can take two forms. None, which think of it as a number that you haven't initialized, right? And you will eventually initialize them. So this option can take the form none, which means I haven't initialized it yet, or sum of int, where you know exactly, okay, that number will take number 5, so it will be sum of 5. And the type of this is not an integer, it's a type of option integer. That's why you need to do .get to kind of unwrap into integer. All right, so does it help with the explanation? All right, awesome. Okay, so let's do a 5 minutes mental break before we move on to the next concept, which give the power to our recursion. This concept is called tail recursion. And the reason why I say let's do a 5 minutes break is this is one of the most important intro concepts for functional programming, and you end up using it a lot. And there's a likelihood that I will ask you to implement tail recursion for the exam, right? So let's do a quick coffee break. If you need coffee, go get coffee. If soda make you awake, do that. We will be back in 5 minutes, 12:55, if that's okay. I assume silence mean yes. So let's meet back at 12:55. Let's go freshen up. Make sure you get caffeine or whatever thing that would make you wake up. It's about 5 to 6 more slides, but it is a lot of new content, and that content involve recursion. So I want to make sure you have the mental break in the middle. All right, we'll meet in about 4 to 5 minutes. All right, so now that we are all hopefully back, let's go into the concept of tail recursion. Here is what does tail recursion do? So let's think about what are the classic example of recursion? The factorial function. Anyone here not? Anyone here familiar with the factorial function? You should, well, hopefully you all are, right? This is basically the same thing as n with this bang, n factorial. That's basically n multiplied by n minus 1, multiplied by n minus 2, multiplied by everything up to 1. So let's see how we evaluate factorial. We can write it this way. Factorial of n, return an integer. If n equals 0, return 1. Otherwise, return n multiplied by factorial of n minus 1. So how can we expand this? Basically, we will actually expand the factorial of 4. I've started writing, right? So this will be a little bit taking up some room. Factorial of 4 equal what? If 4 equals 0, 1 else n multiplied by factorial of 4 minus 1, right? This means that you have if, what is 4 equals 0? What does it evaluate to? What does 4 equals 0? You are awesome. That is false. If false, 1 else n multiplied by factorial of 3, right? And then you continue on, right? Is equal to n multiplied by factorial of 3, on and on and on. And you keep continuing. Right? So do you see how this expression would keep growing? Expression would now keep growing. We'll keep doing factor of 3. What is that? If 3 equals 0, 1 else 3 multiplied by factorial of 3 minus 1. Evaluate that. then 3 multiplied by factorial of 2, which means that it's going to be 4 times 3 times if 2 equals 0, 1 factorial of 2 minus 1, blah, blah, blah. Eventually, you get 24. So the expression keeps growing. And during this time, what will happen is scalar need to remember all this value, right? It basically keep growing the expression, expanding the expression, and remembering all this value. What do we know about having to remember many things? Anyone here avoid biology because you have to memorize so many terminology? Raise your hand. Myself included. Yay. Right? So, I mean, that's that. I guess that's my nature. I would say that's human nature, but that's not true. There's people who appreciate biology and like remembering things. But myself, for example, I have limited memory, right? So this means that scalar, if they have to remember all these things, it took some toll. Basically, it would take DRAM. When you buy a computer, you have limited memory. How many of you here open 30 Chrome tabs and then realize your computer gets slow? Or 40 Chrome tabs? Yeah, it happens, right? Because each tab, if you go to Task Manager or if you go to Mac and type in the command top in terminal, it actually would open up and see who is using all the resources. It's one of those system monitoring tools. And you see that there'll be a lot of Chrome. Each one of them takes some memory, right? Because they actually consume your memory that you buy for your computer. And things will get slow. So this is bad, right? So the normal form of recursion can be bad for performance. The question we have here is, well, can we rewrite the code such that it doesn't really grow? Can you do some partial computation in the middle so you can collapse some of these multiplication and function expansion on this thing? And this is called tail recursion. It's there. So basically, this is there for performance, right? So here's a factorial using tail recursion, right? Using tail recursion. What do we do? Well, in the older version, we have this, right? 4 multiplied by 3 multiplied by 2 multiplied by 1, which seems okay. It's only 4 numbers. You don't have to memorize much. But let's imagine Fibonacci of 100, right? If you have to do Fibonacci of 100, imagine how many of the ones and zero you ended up with when you expand them all. It's a lot. You're gonna have a lot of 1 plus 1 plus 1 plus 1 plus 1 plus 1 because you expand all that Fibonacci number. So let's use factorial, but in a tail recursion fashion. When you have 4 multiplied by 3 multiplied by factorial of 2, what can you do? Can you collapse anything here? Is that a yes or a no first? Is it possible to make it shorter? Yes, exactly, right? Because what's 4 multiplied by 3? 12, right? Right? So you can collapse this. This is a concept of tail recursion. You have what we call accumulator. What does accumulator mean? What is the definition of accumulator? It collects something. Awesome. That's the definition, right? Over here, I have accumulator called product. It collects partial products, right? So if I can have this accumulator, what can I do? I have the tail recursion. You start at the beginning. You want to do factorial of n, right? So n is the number you want to find factorial 4. And initially, our accumulator is 1, number 1, because 1 multiplied by something would give you back that number. Right? It's the identity number for multiplication. So you start with 1. 1 is the initial condition. If n is 0, you're done. You return the results. If not, you do the tail recursion. You do factorial of n minus 1, but you start to accumulate all these partial results. You collect results along the way while you call this function. So you do products multiplied by n. Right? It collects partial results. So let's break this down into using the example of factorial of 4, right? So factorial of 4 is tail fact of what? What is tail fact of n and 1 when n is 4? What is tail fact of n and 1 when n is number 4? It's tail fact of 4 and 1, right? Exactly. So what is tail fact of 4 and 1? Is if, my bad, typo. If 4 equals 0, return product right now is 1, else return tail fact of what is n minus 1? 3. Yep. And what is products multiplied by n? 4, right? Product is 1, n is 4, so you do tail fact of 3 and 4. What does it do? Basically, if 4 equals, yep, sorry. This is false, right? So you're gonna do tail fact of 3 and 4. What is tail fact of 3 and 4? That if 3 equals 0, 1, but my bad, not 1. What is product for tail fact of 3 and 4? That's 4, right? Else, you do tail fact of what? What is the n minus 1 here? 2, correct. And what is the new products multiplied by n? 12, right? Because now your product is 4, n is 3. What is 3 multiplied by 4? 12. Again, this is false, so you don't return this. You go here. That's equal to if blah 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 2 equal 0. What is product now? It's 12, right? Else you do tail fact of 1 and 24, and you go again. So look at this. Every time you call the function, every time you call this recursive function, you already compute your results. You have everything you accumulate so far, right? That's why we call this tail recursion. And if you haven't realized, I also use less room on my slides to write everything out too, because every time I go one function call, I don't have to keep the old number. I already have my accumulator that by the end, once n becomes 0, what will I return for factorial of 4? What is product? What is the product of tail fact 0, 24? 24. You got the result already, so you return right away. Right? So here is the general definition of tail recursion and some of the differences. The difference here is, well, first of all, a typical approach to writing a tail recursion is the last line before the function, basically the return thing for the function is a call to another helper function. It's not the function itself. We call this a tail call. We call this a tail call, right? This is called tail recursive function. And the benefit here is if you're in file processing, no, not file processing, that was the old name, system skill, the same class. If you're enrolled in system skill before, one of the modules we talk about assembly, And inside that assembly modules, we talk about every time you call a function, you have to allocate the function in the stack frame. And that's a lot of overhead on a computer. So the tail recursion get rid of this stack frame. You can recycle them. Basically there's a less overhead on a function call. On top of it, from the compiler point of view, so this is basically a little bit more advanced. Basically, when you compile the program, when you have a program, compiling a program means that you have another different program. If you use Java before, is that step when before you hit run, what does the IDE have to do? It actually analyze your program, look at it, and convert every single line of your program into assembly so that you can run a program. That's called compiling a program. A compiler can optimize your code, make it even faster. So if you write a program in the tail recursion manner, it allows you to actually have the compiler to reduce the burden. It's easier to optimize your code because the compiler look at your code like, oh, I know exactly what you're trying to do. So in the previous example, this product, this variable that we put in is called the accumulator. It accumulates the answer, so we can actually do partial computation while we're waiting for the call to return. Right? Any questions so far before we go through another example? And here is an example. I want to write a function that sum everything in my list, right? So I have the recursive function. If xs is empty, return 0. Otherwise, do xs.head plus sum xs.tail. So that's our function from last week, right? Not summarize. Do a summation on everything in your list. You can rewrite it using tail recursion this way. The first step, at the end of the day, you call the helper function. Your helper function here is called tail sum. That's your input, list xs. This is your accumulator. Why do I start with 0? Because instead of a product, you multiply things. You are doing a summation, adding things over. What should be an initial condition for adding? You start with 0, nothing, and you accumulate 0, 10, 15, 13, 18, things like that, right? So our tail sum takes in two inputs, the list itself and the accumulator. Accumulator, because it's a integer, so you say, hey, it's going to return an integer. If my list is empty, what do I return? So if my list is empty, what should I return? Can someone tell me what do I return here with the code I just listed? Yeah, your accumulator, because by the time you go through the list, the assumption is you're done. You accumulate everything so far. So you return the accumulator. Otherwise, this is the recursion. By going through the rest of your list. In the meantime, accumulate by doing acc plus ys.head. Start accumulating along the way while you're calling this function, right? So you see from this example, you can kind of expand on the fact that, hey, there's a pattern here that you can kind of like develop the same tail recursion using pretty methodical approach. So these are common things in tail recursion. When we are at the base case, the helper function, most of the time is done. So you just return your accumulator, right? Most of the time when you have tail recursion, and this is actually why they call it tail recursion. When you're done with the recursion, you have the results already, so you return accumulator. The accumulator store all the partial computation that we've seen so far, right? It store all the partial computation that we've seen so far. And the tail call is really, really similar to just a typical recursive function. And this is similar to a while loop, right? It's similar to a while loop. You go through the loop, accumulate, go through the loop again, accumulate, go through the loop again, accumulate, and when you are done, you already have the result. So you go out of the while loop. Why is that the case? You can have a tail call that actually call another function as well. So you can make tail recursion a little bit more complex. Okay? The first two bullet points here is more like a general guideline. The third bullet point is like, okay, can we do something else? It is actually a powerful tool that you can call more functions, right? And with that, this is in class exercise 3. We already posted on Canvas. And please make sure you submit them. And before we leave today, we have more things to do for in-class exercise 4. I'm going to post it again, as I said, right after this in about 5 minutes on Canvas. But here is the overall explanation. First, write a function called find. You have the input, which is a list of pair, integer, and string. Integer and string. And another input called the key, which is an integer. So if your xs is 1, hi, 10, hello, 5, cat, and your key is 5, this should return cat. An option of cat, actually. It should be an option of string. This particular function would kind of get you practice on using an option. It should return none if nothing match. So let's say the key is 4. Our list has nothing that has a value 4, so it should return none. If the key is 10, it should be an option of hello. Another function is def reverse. You have the list, you return a list, but you flip the order. But in this case, let's use tail recursion. So let's practice tail recursion by this first function called reverse. Another a little bit more challenging function to practice is Fibonacci. I want you to, for both of this, use tail recursion. Why is Fibonacci more interesting? Because you accumulate two things at the same time. Fib of n minus 1 and fib of n minus 2. So that's your third task of the day. Any questions so far before we wrap up today's lecture portion and we move to Discord? No, for exercise 3, use whatever you want to use. Basically, this is the gradual learning curve that we're gonna run into. In class 2, use just a typical, almost predefined steps that we have in the handout. In class 3 would be kind of practice with the functional programming in general, no need to use tail recursion. In class 4, now is the time to practice both of the things we learned today, option and tail recursion. All right? Okay, so now that we are done with the lecture, let me first stop the recording.